like even though I'm on a seminar, the axioms are that everybody is welcome to use the cell phone, but not in this room. If you need to use the cell phone, please go out and come back when you are ready. And also, if you behave and pay attention, then you are welcome to come to celebrate, hopefully, in the unlikely event that Blair will pass, and lunch at the Evelyn restaurant in Broadspeed at 12:30. So right after the defense, and also if he doesn't pass, if Blair doesn't pass, we also go that's to cheer him up. Oh, hi, I got the tax. And so right after the defense, I will ask people whoever wants to come so we can make it to the basement. Thank you. Go ahead, Jeff.
Okay, thank you, Dr. Z. So I think that I'm going to uphold a time-honored tradition among experimental mathematicians, and I'm going to spend a couple of minutes justifying what it is we do, since I don't think that's necessarily clear to everybody. Yes, I am recording. If you look at the Wikipedia page for experimental math, you will find most of this quote. It omits the last sentence. But this is by, the great mathematician Paul Halmos, who, really says math is not a deductive science. Math is at its core inductive. We experiment, we play around, we look for patterns, and then we figure out what's going on, and maybe later we put together an inductive proof. This was also said somewhat more succinctly by Dr. Z, who blames Euclid for ruining mathematics by trying to turn it into a deductive science. If we wanted to be philosophers, we would be philosophers. But really, what does the scientist do? The scientist sees something cool in nature and tries to figure out why it works that way. They state a hypothesis, they design an experiment to test what they're doing. They then, conduct the experiment, gather some data, and either they support or they refute the hypothesis, and then they refine and repeat as needed. And if everything goes well, they get a first author paper, they have a theory, they have a law, something like that. Well, what do? We do pretty much the same thing. We see something interesting going on, usually with mathematical objects, so somewhat abstract perhaps, but we also, want to know what's going on. So we design an experiment, we collect data, we have our computer run as many cases as it can. Hopefully, we can analyze what's happening. We can, come up with a theory as to why this is going on. And we end up with a pattern, a conjecture, a theorem. And I think that maybe the place where science and experimental math have their biggest overlap is mathematicians have this great respect for any conjecture that's been around for a really long time. Nobody's disproved it, nobody's improved upon it. And they really, it's not a theory, it's not a theorem in the math sense because it hasn't been proven, but people have a lot of respect for that. And that's really what scientists mean when they use the word theory. So we're not so far off as one might think. Okay, so the specific things that I'm going to talk about, I did 3 separate projects over the last few years, one of which is trying to find minimal circuits for Boolean functions. These are just the small ones because computers can't deal with too many cases. And then a project on discrete subcubes of the n-dimensional cube, which is based at least in part on Professor Thanadapananda's paper from 3 years ago. And then a project on the combinatorial game Juniper Green. And in all these cases, the objects that we're looking at experience some kind of exponential growth. And when you're using a computer to deal with an exponential problem, it's like playing a video game. You know that you're going to lose eventually. The question is, how long can you hold it off? Yes.
In the first case, it is W exponential.
That's fair. That's fair. So, the problem is we know that we're going to lose the game. The question is, how long can we hold out? And in all these cases, we're going to use Dr. Z's, overlapping stages technique, which basically says, okay, write a simple program. Brute force, just use the definition of the object. It won't get you very far, but it will get you something. And then we try to find some clever way to make it faster. Maybe we prune the number of objects that we're looking at. Maybe we can find some symmetry consideration. But whatever we do, we're going to check to make sure that whatever cases we could generate with brute force match the clever technique. And that's going to give us more faith that the subsequent answers are correct. And then we're going to repeat this process perhaps several times until either we have enough data to answer the question we were trying to answer, or we just run out of, optimizations that we can figure out. Okay, on to the first project. So when we're talking about Boolean functions, we have K is the two-element set, which is false and true, and any Boolean function from an n-dimensional space of K into K is going to be a Boolean function. And in practice, we can use any two-element set. Most of the literature uses 0, 1, but for reasons that I'm going to explain in a moment, we tend to use -1, 1 in our implementation. And the reason we do that is because it makes it easier for us to reference subcubes. If we look at the standard Hamming cube for K3, this is a subcube, it's an edge. And in most of the literature, you'll see this written as like 1 star 0 or 1B 0, 1 dash 0. But Maple doesn't like any of those. Maple likes numbers. So by relabeling into -1, 1, we can write this as 1, 0, -1, where in our Maple implementation, 0 is typically the wildcard. This two-dimensional subcube is now 1, 0, 0. And again, we see 2 dimensions, 2 wildcards. That's going to be important later. Okay, and what do Boolean functions look like? There are several different ways that we can think about them. Just as a subset of the n-dimensional space, these are the points where the function is true. We can write that out as a set of points explicitly. This set of points translates directly into this disjunctive normal form. We're just saying, if I meet one of these 3 conditions, I'm in the function. I can reduce that expression, and I can also come up with a Boolean circuit which evaluates it. All of these are equivalent representations. And in this project, we're going to be looking for circuits which are this representation, which are as small as possible to compute a particular function. And it's easy enough to come up with a circuit to compute a function. Obviously, if you just take the set of points, translate directly into a DNF, that will give you a circuit. You could code that circuit. You could use Quine-McCluskey or some other algorithm for reducing the expression. That will give you a better circuit. But to be sure that you have a minimal circuit, you have to test all smaller circuits and make sure that none of them accidentally computes the function. And that's, where both the fun and the difficulty come in. So we use straight line programs as, yeah, Lucy. Oh, this is a function. So, these are 5 different representations of a single function. And there are 2 to the 2 to the n functions for any number of variables. Okay, so we use straight line programs. This is really kind of what circuits do. It's a programming method where there are no branches, there are no if-thens, there are no loops. Very simple. And in our definitions, a gate can be any one of the 10 non-degenerate functions on 2 variables. So the constant functions, one of the variables, and the negation of a variable, those are not gates, but any of the others can be. And this is kind of what that looks like. These are the 10 functions of 2 variables that actually depend on both variables, and we just kind of numbered them 1 through 10. And these are the other, kind of weird line formats. First, we read the inputs. So the first n lines are always going to be read in your inputs. And then for the 0 gate functions, we have special code for that. Those don't get used in any real circuits. So what does this look like here? This circuit that I had on the board before, we need to do 5 things. We need to read in our 3 inputs. We need to take the second and third of those and OR them together. And then we need to take the result of that gate or with the first and AND it with the first variable. And that gives us, this program in our Maple code. So that's kind of what our format is going to look like. So the thing about looking for these, yep. Sure. Right, so this 5 is because it's an OR gate. Yeah, and the 1 is an AND gate. So that's all these encodings are. So the issue here is that we're looking for some largish number of needles in a very large haystack. So, the experimental mathematician tries to reduce both the number of needles and the size of the haystack as much as possible because our computers can only run so quickly. So the first thing that we do is we look for equivalence classes of functions. Tillman Peace actually has a web page where he defines big equivalence classes and small equivalence classes. Big equivalence classes turn out to be more useful for me. So a small equivalence class is the same thing, except that it only allows negation of variables, not permutation. But here, if I have assigned permutation of variables, and that will get me from one function to another, I say that those two are in the same equivalence class. And this has the advantage of reducing the number of functions for 4 variables from 65,000 to 402, which is, definitely a more acceptable number of needles. There's really no way for me to go hunting 1.2 million functions, so I didn't try that. I would not want to look at that output file regardless.
So everything is known. For n equals 6, it's not known.
I think for n equals 6, I think he may have 1 or 2 more terms here, but
Oh, that's all Boolean functions.
yeah, I mean, all Boolean functions are just 2 to the 2 to the n. So yeah,
I think that is not up to 30.
Could be. So, I think that one of the things in order to justify this is if I have a circuit that computes one member of a big equivalence class, I want to be able to say, hey, I can get any other member of the class by, just doing some simple transformations. It is guaranteed to be a circuit of the same size because what I'll do is I'll just leave the circuit in place. I'm just going to change the numbers of the inputs according to the permutation of variables. And if I have to negate a variable, I can just switch the gate type. I don't have to switch the number of gates or the structure of gates, just, what gate type it is, because I have all 10 of the non-trivial functions available. So in order to take advantage of these big equivalence classes, I need to pick a representation, a representative of each class. And then I'm going to hunt just the representatives and know that I have a way to get circuits for the other elements of the class if I need it. So again, we're going to follow Peace's numbering scheme where he numbers these functions. We go from 0 to 2 to the 2 to the n minus 1 because that seems like the right way to number them. And specifically, the ordering scheme is just take the inputs and line them up in numerical order. If you think about these as 2-digit binary numbers, this is just 0, 1, 2, 3 down the left side. And then the function number is read this as a binary number from top to bottom. So these are just the numbers 0 through 15. So that will be the ordering that we use on those. So the next question is, how big is the haystack? And this is where we run into a bit of a problem. If you just look at the syntactically valid 7-gate circuits on 4 variables, there are, a 19-digit number of them. And obviously there's no way that we're going to get through that many. So we have to start chopping very quickly. So the most obvious thing, yeah.
So 7 is just illustrative, or
7 is because that turns out to be the maximum circuit complexity of a 4-variable function.
Is that an outcome of this investigation?
It's been known for a while. I mean, as I'm going to mention later, Saarinen in a paper that he published in 2006 kind of just mentions off the cuff, oh, by the way, these are the numbers of all of these functions and the maximum gate complexity is 7. I think he was talking, it was a secret paper, and he was talking about something like, you know, how do I break this particular thing? How secure is it? And he needed that information. So, but yes, I also, you know, noticed that I could get everything with 7 gates, but that's something that's been known for a while. Okay, so the first thing obviously is if,
You're gonna know again, the frequent, the maximum frequent baseline program for boolean function with and Bible.
I don't think it is. I looked for it. I don't have enough terms to really, you know, make a meaningful contribution there. I think you need at least 6, and I've only gotten as far as 4. Well, I only know about 4.
Okay.
So,
When you say 7, that does not include the input gates,
that does not include the input gates.
So 7.
So seven actual gates, and I also don't include not as a gate. So 7 gates where I can use any function. Okay.
Yeah, with the model of the 10.
Yeah, with the model of the 10 non-degenerate functions. Yep.
Then you do
Mhm. So, you know, the most obvious thing to do is if I don't use the output of a gate, it shouldn't be in my circuit. You know, fortunately, the recursive algorithm that I use to generate circuits took care of this for me. Because what I do is I generate, you know, the top gate last, or the top gate first, and then I generate 2 subcircuits. And if the subcircuit is empty, that really just means that it's one of the input variables. So the next obvious thing is, let's make sure that my 2 inputs for the gate, the first one is lower numbered than the second one. If the 2 inputs are the same, then I don't really need that gate because it's either a constant or it's just, you know, the variable that's coming in or its negation. The other thing is, if a gate has inputs like 6 and 3, I can always reverse those and just switch the gate type if it's one of the asymmetric gates. So that's a couple of optimizations. Slightly less obvious is to get rid of the mirror image circuits. So what I do in my code is I essentially say whatever the left subcircuit is, that gets, you know, at most half the gates. Because if I had 6 gates on one side and 2 gates on the other, I could always swap that and just, again, switch the gate type. So this reduces the number of gates I have to find and the number of circuits I have to compute. And then, you know, the last thing that I do here, which, you know, I kind of leave as an exercise to the reader, is if you have a gate whose child and grandchild are the same input, you could either switch that into one gate or eliminate it completely. This is not hard. So with all of that, I managed to get to the point. Yeah.
So how is this counting the size of the subcircuit? This is the number you said. You always choose them in order that the left child.
Yeah, the left child is at most half the gates. So what I do.
But when you say the most half gates, the same gate could be contributed to both the left and the right.
Yes, and that's actually what I'm about to get into next. You know, is my bridge too far? You know, I did not allow for fan out of gates, and later when I built that back in, you know, I hit a couple of walls. So, yep. Yeah, so, you know, and one of the things about that is that really, if you're talking about gate reuse, the fact that, if I go back up here for a second, I allow these inputs to be any number less than the number of the current gate, means that I am, you know, kind of including that in the model. Okay. So again, you know, what Professor Sachs was just talking about here is, you know, oops. Here we go. Is that, you know, my initial implementation, I did not allow for gate reuse. I did not think that was going to matter. Because these are very small circuits. How could it possibly matter? It turns out it does. And again, you know, I found this paper by Saarinen where, you know, just kind of as an aside, he talked about the number of functions of each gate complexity. And, you know, I looked at my numbers and I looked at his numbers, and apparently I have a few big equivalence classes where I only found a 7-gate circuit, but I needed a 6-gate circuit to match his numbers. So in theory, fixing that is easy. All I have to do is, allow for gate reuse in an unlimited way. And in practice, that gave me too many circuits, because Maple does not like having 42 billion of anything in memory. So I tried a couple of things here. One of the things I did is at each level of the recursion, I threw away duplicate circuits. That is to say, if I had 3 different circuits that computed the same subfunction, I just kept one of them. But of course, that doesn't really work, because what if there's a particular gate in one of the functions that I threw out that the other side would like to use? So I'm still off by a little bit. And here's the little bit. So I believe that 2 or 3, depending upon which ones they are, of these 7-gate big equivalence classes should actually be 6-gate. But this is kind of the distribution here. And if you look at this in terms of total number of functions, these are off. I think this is supposed to be about 2,300 or 2,400. I don't remember the exact number, but some of these should be here. Saren and I also disagree on the first 2 numbers, but that's because he considers not to be a gate and I don't. So he has we have a difference in 0, 1, but that's trivial.
So we have different conventions.
Right. So for 0 versus 1, it's a question of convention. That I'm not worried about. For 6 versus 7, I think that's the actual flaw that I was talking about. So, which functions turn out to be hardest? Just in the 3 variable case, because these are the easiest ones to talk about, there are 3 equivalence classes that have the maximum complexity, which for 3 variables is 4 gates. The one that finds are exactly 2 of these true, the majority function, and this weird function where either, this input is either exactly 1 input is true or x1 and x2 are true. So those are the weird ones. And the majority function, here is the circuit that I happen to find for it. There are certainly others, but if there are any others that compute it, they have to require at least 4 gates, because none of the 3 variable ones did. And, in the future, I do hope to, finish up and find this discrepancy. It may require, a serious rewrite. And this is a particular circuit that I'm worried about. I think this gets back to what Professor Sachs was saying, is if I have a circuit where I reuse this gate on the 2 sides, I have to generate 3 here and 2 here, and then have that work. So this is probably going to require switching things over into Python or something more efficient, so that I can actually store tables of all the 3 variable functions and then work through them one at a time. Okay, so I think that's. Yeah.
So you mentioned this, the symmetries.
Yep.
Of the boolean functions. There's also symmetries of the circuits themselves.
Yes.
Which one can, I guess, if you apply any of the symmetries of boolean functions to the circuits, you get symmetries which enable you to eliminate.
Right. I do use symmetry to eliminate, in the sense that, if I have 2 subcircuits of different sizes, I'm only going to generate them in one way, not the other. And if I'm generating a 2-element circuit, which I'm usually doing on one side, that's got to be a chain of gates. That can't be anything more interesting than that. So, I think that for the most part, that all gets taken care of kind of automatically. I'm probably missing some cases, like if I have a circuit that's balanced with 3 gates on each side, I might generate a couple of different equivalent forms. But, I think that the amount of effort that it takes to find those and eliminate them may be more work than I'm doing just by computing them. So,
that's the most interesting function that goes with this, the maximum number of gates. So you look at something like this, you mentioned for N equals 3, right? For N equals 3,
right.
What are the function?
Right. So
how does it look? The function with maximum
For four, well, there are a bunch of them. I mean, there's something like, I think 15 classes that have that. The majority function is still one of them. As a matter of fact, the majority function seems always to be one of the hardest things to compute. So I mean, it's usually a pretty good benchmark. We're actually going to see that when I talk about monotone functions in a second.
Okay. But the majority function, for an arbitrary number of arbiters, is probably not that complex, right?
It's usually one of the hard ones. I mean,
Yeah.
majority is an annoying function to compute just because you have to, check a lot of things. I mean, adders take up a lot more circuits than ands and ors. You want to think about it that way. So, we next, and I'm going to try to do this quickly because I'm a little behind schedule here. We looked at monotone functions where, a function is positive in a variable if changing that variable from true to false will never change the function from false to true. I may have said that backwards. Yes, if changing the variable from true to false will never make the function go from false to true. Negative is the other way around. And a function is monotone in a variable if it's either positive or negative. And a function is positive, negative, or monotone if it meets that parameter for all of its variables. So, I did manage to get my first OEIS sequence out of this by finding the subsequence of the big equivalence classes, which are monotone. So that was, a nice little moment. And, one advantage that we have of looking at these functions is that we can use just and OR gates for positive functions, which means that instead of our exponential growth being 10 to the number of gates, it's 2 to the number of gates, which is much easier to deal with. Also, if you look at big equivalence classes, there are only 210 5-variable big equivalence classes that are monotone out of the 1.2 million, which meant that hunting for them seemed like a reasonable enough thing to do. It's also interesting that the number of big equivalence classes, this is just one of those facts that I enjoyed, happens to be describable by the Dedekind numbers. And the reason for that is they also describe the number of antichains. So if you think about your Hamming cube as a partially ordered set with all true on the top, if you specify an antichain, every the upset of that is a unique monotone function. So that's kind of why that correspondence is there.
So you are restricting yourself to monotone gates.
Yes. And yes, the monotone circuit complexity and the circuit complexity are not the same. I think it was what Razbarov in 85 showed that there could even be an exponential gap there. So, I mean, they're not the same, but they're cool to find. And, again, the 13 gate function here is in fact the majority function. And I could not find a better circuit for that. And again, I'd like to, confirm this result with gate reuse if I have time. Okay, so that's it for Boolean functions. I think everybody got their questions in while we were talking. So maybe I'll just keep on going. So next case is we're looking next at subcubes of the n-dimensional cube. And, the statistical moments of a random variable or a combinatorial object X tell us something about the shape of the distribution. And in this project, the thing that we're looking at is we're looking at all Boolean functions on n variables, and we're looking at the number and sizes of implicants contained within the Boolean function. So if we look at, x1 or x2, it has 3 implicants with 1 point, which are the 3 points where it's true. It has 2 implicants that have 2 points, which is x1 and x2. And when we think about Boolean functions as a subset of points, the implicants are just subcubes of that Hamming cube where every point is in the true set. So the previous example would have 3 points and 2 edges. That's kind of how we're going to think about it. And we're really going to we're going to kind of forget about the fact that these came from Boolean functions for kind of the rest of this part of the talk. And we're going to just talk about these as subcubes of the larger cube. So Pananda wrote this lovely paper 3 years ago in which he used linearity of expectation and, a kind of inclusion exclusion argument to find some of the moments of subcubes in the n-dimensional cube. And in the case of, k equals 2 and r equals 1, we're talking about two edges. Well, if you have two edges, what can they do? They can either be disjoint, they can overlap completely, or they can intersect at a point. So if they're disjoint, there are 4 total points. The probability of all 4 of those appearing is 1/16. If they touch at a point, then the probability of all 3 of those points appearing is 1/8. If they are overlapping, then it's only 2 points. The probability is 1/4. And if you add all of those up, what you actually get is you get the second moment. So that's kind of the way that argument works. And he was able to kind of extend this and come up with these lovely formulas for the mean and the second moment for r-dimensional subcubes and n variables. So these are kind of general formulas. And the paper also includes the first 3 moments for edges and the first 2 for squares and the first 1, I believe, for cubes, because trying to enumerate all of the different ways that edges can overlap or not starts to get very unwieldy beyond that. So here's what we decided to do. Our data structure thinks about r-dimensional subcubes as row vectors, essentially. So if you have some r-dimensional subcube, what you do is you just set n minus r of the variables to some constant and you let the others roam free. So you end up with 3 wildcards for a 3-dimensional subcube. And what we're looking for is we're looking for a weighted count of these. So kind of our natural data structure is if we're looking for the kth moment, then we just set up an array of k rows, and n, which is really symbolic, is going to be the length of each row. And if these are r-dimensional cubes, then we have exactly r wildcards in each row. So for any specific n, there are kind of, this many of those. And for each one of those, we can just, figure out in this configuration, how many points are there, and then we just add 1/2 to that number to our running total, and by linearity of expectation, we end up with the moment that we're looking for. So in order to try and compute this in some kind of reasonable amount of time, we came up with this idea of kernels and remainders. So the kernel is the set of columns in this matrix that contains any wildcards. And we're going to call a column active if it has at least 1 star. And we can't have more than k times r active columns because that's the total number of wildcards in the entire matrix. And we are going to have this idea of a canonical form where all the wildcards are kind of shifted to the left side of the matrix. So what we can do is we can say, okay, if we take all of the wildcards and compress them over onto the left side of the matrix, well, there were only like n choose a ways that we could pick the active columns. So if we do some kind of brute force-ish calculation on this now small matrix, we can just multiply by that, and that number of symmetries will get us back to the number we're actually looking for. And we do the weighted count, every matrix gets, credit for whatever the probability is of all those points existing, depending upon the overlaps. And, we only have so many choices for the leftmost columns, which are the kernel, and we divide them into equivalence classes by kind of saying, well, we permute zeros and we permute columns and rows, and we, switch zeros and ones, and, all those kind of have the same flavor to them, because what we're interested in is the structure of where the wildcards are. And then what about the remainder? Well, the remainder is going to have, nothing but zeros and ones, and in that remainder, we can look at if every single column in two remainders matches, those two intersect. And if there are any differences, then it doesn't. So we can think about how many different ways are we going to be able to set those bits. Most of these have distinct rows. I mean, this is just the number of this 2 to the n minus a is the number of binary strings that could appear as a remainder. If we pick k of them and order them, however, this number tells us how many different remainders we can have with all of the rows distinct. And in the easiest case, we have just one remainder repeated, k times, and then we're only filling in one of those strings. So that's kind of the range of what can happen over there. And then, all we do is we just generate the finite set of matrices. We figure out how many points are in each matrix based on, the matrix and the set partition of the rows. And then we kind of add all those up, and that gets us some results. So in the vein of overlapping stages, one of the things that we did, of course, is we made sure that for the first 3 moments, our results matched the ones in the 2020 paper. And then we were able to generate 3 more moments for edges. So these are the 4th raw and central moments for edges. And these are just kind of, they're all polynomial in n and 2 to the n. And they all have, coefficients that may or may not be interesting to anybody, but here they are. 5th moments get a little bit uglier. And then we also managed to get out as far as 6 moments. We don't leave that there for just long enough for you to decide you don't want to read it. Okay. And same with this one. And from these moments, it is actually clear if you play with them a little bit that we get the 3rd through 6th scaled moments doing the 0, 3, 3, 0, 15, which indicates that this is a normal distribution. So we kind of looked back in the literature, and 30 years ago, Konieczna proved the asymptotic normality of these XRs in kind of a general case where we don't even have to have probability a half. But our approach inspired a new proof by Svante Janssen, who was kind enough to co-author a paper with the 2 of us. And it was for this specific case, but it was kind of an elegant proof. We're happy with it. Okay. More polynomials that I don't think anybody wants to look at. So we confirmed that our results match the 1st and 2nd moments with the original paper. And then we were able to come up with the 3rd moment and the 4th moment for squares. And then, the 3rd raw moment for cubes. And yes, that's an ugly number. That's a slightly less ugly number. Okay. We then decided to kind of move on to mixed moments where, we're looking for like maybe edges and squares. And these are interesting, at least in part, because they provide some insight into the correlation between subcubes of different sizes. And, we did some brute force things. Then we used our Maple code to generate a bunch of moments and do calculations from there. And we kind of came up with some moments. So these are mixed moments for the first few values. And this formula is, kind of one of my favorite things. I left this unsimplified form here. This is a generalization of the 2nd moment formula to the mixed moment. And in this unsimplified form, this is really the number of ways that you can set the bits in the kernel. And this multinomial coefficient here is the number of places that you can place the wildcards. This number up here is the number of ways that you can set the bits for the remainders. And this number down here is the total number of points in the configuration. And for this whole summation, we're thinking about I as the dimensionality of the overlap between the 2 subcubes. So a zero dimensional, if I is zero, we're saying that the two subcubes intersect in a point. If it's two, they intersect in a square. And then this rest here, these are just the number of non-overlapping configurations, because we take all the configurations and subtract out everything that overlaps. And we divide that. Again, this is going to be the size. This is going to be the number of points in that configuration if there's no overlap. And this is just a simplification. So using, I think I just said that, but using this, we were able to get, some much larger moments because this is easier to compute than what we were doing before. And this kind of let us figure out some correlation stuff. So the correlation of two random variables is, this lovely formula. And it seems reasonable that if you're looking at subcubes of different sizes, that the correlation kind of has to be one, because the more points you put in a function, the more edges it's going to have. So that doesn't come as a surprise, but it seems kind of natural to wonder how quickly do we approach one. So here are the first few correlations that we calculated. And one of the things that I kind of noticed off the bat here is that these coefficients are the difference between the size of the subcubes over 2 squared. So that's why 1/4 and 4/4 and 9/4 and 16/4. So that's one of the things that I noticed, but we wanted to find formulas for some of the others. It's obvious that the coefficient on 1/n has to be negative because the correlation can't ever be more than 1. And it is in fact always r minus s squared over 4. The thing is, we wanted more of these, so I just calculated a whole bunch of these as far as I could, and then took those coefficients, threw them into a big matrix, and tried to fit polynomials to them. And I mean, you can obviously fit a polynomial of degree 1 less to anything, so we had to be at least 2 degrees less than the number of rows or columns. And this is what we came up with for the first few. I think I actually have the 4th, 5th, and possibly 6th ones on my website, but they don't really fit on a slide because the coefficients get out of hand quickly. And just a couple of observations about these. The degree of every polynomial is twice the exponent in the denominator on n. It kind of makes sense that these polynomials are uniformly 0 when r equals s, because we know that if we correlate a variable with itself, that's always just 1. So all those have to vanish. And it's also comforting that they are symmetric in r and s, because the correlation of xr, xs should be the same as the correlation of xs, xr. Okay, so questions on that? I kind of went a little bit faster than I wanted to, but.
So on the negative, or for specific elements, the coefficients of the power of 1/n.
No, they're not.
Okay.
There are a couple of plus signs that sneak in, but the 1/n always has to be, just because, because that's the one that's vanishing the slowest. But after that, it can be either way. Yeah.
So, one general question. So, are there any empirical phenomena, that you observe empirically in all the data you generate that suggests something interesting to be explored?
I mean, I would like to know why these coefficients are the way they are, but I haven't gotten there yet. So, I mean, just looking at these numbers does not really give me a lot of insight, because I don't know what, this number means. So that's going to require pulling numbers apart and maybe looking for sequences and numerators or something, trying to find something in the OEIS that matches it. Okay. I have not very much time for this last project, so I'm going to skip some of the definitions. So we're talking about the combinatorial game Juniper Green, and just, really quickly, a combinatorial game is an open information game. So most card games do not count because you cannot see the opponent's pieces. The game is finite if it's guaranteed to produce a winner. after some finite number of moves. So if you think about tic-tac-toe, because every move uses a square, you can kind of think of your space of possible outcomes getting smaller at every stage. So it's finite, but checkers isn't, because if two people have kings on the board, they can just kind of move those around forever and not get anywhere. So that's the difference there. And a combinatorial game is impartial if a move that is available to one player is also available to the other. So a game like chess would not count because you can't move your opponent's pieces. Kind of the stereotypical impartial game is NIM, where you're removing objects from one or more piles, and it will come up in discussion later. So one of the things is you can model any finite combinatorial game as a directed graph, where each node represents a position of the game, and you have an edge from one to the other if it's the consequence of a legal move. Note that the underlying graph for this diagram does not need to be a tree, because you might have different sequences of moves that get you to the same position. Like you can picture a player in tic-tac-toe making a move first and then another move third, and they can make those in either order and get to the same place. And we're going to use this notation because we're thinking of the set of moves from a particular position as a neighborhood in this position tree. And if there are no moves available, then the current player loses. So that's that.
It doesn't have to be a tree with any different position tree, so it might be the case where it is a tree.
Okay, I should say position graph. I misspoke, because I just said the word tree, so it was on my tongue still. Yeah, it's a position graph. And we can classify every position as either a P position, which is to say the person who just went has won or is going to win, or an N position, that is to say that the next player is going to win. And these designations do depend on people making the right move. So, you know, if something is a P position, it means that if we both play properly, the person who just went will win. And we can classify every node in a position graph as either P or N, just by saying, hey, if I'm a leaf, there are no legal moves for me, therefore the person whose turn it is loses. And then I go up a step and I can say, well, if there is at least one position below me, which is a losing position for the other guy, then this is a winning position for me. Having done that, I can now say, okay, if all of my children are filled in and all of them are winning positions for the other player, then this is a losing position for me. And if any position remains unlabeled, you just repeat steps 2 and 3. For a finite game, this process is guaranteed to terminate because each leaf has to be the result of some finite number of moves. So that many iterations will definitely get you a kind of this coloring of the entire tree. We do need the concept of a minimum excluded number of a set, which is just the smallest number which isn't in the set, where number here is defined as the natural numbers 0 and up. So we'll be using that. And we define a Sprague-Grundy value as 0 if there are no moves from this position, and the minimum excluded number of my neighborhood otherwise. So in a sense, this includes the information about whether I'm an N position or a P position. If I'm a losing position, my Sprague-Grundy value will be 0. But if I'm a winning position, it can be any positive number.
Yeah,
Yep.
I don't need that. You just gave this.
Right?
The next of them is that, you know.
I understand. But this is the way it usually gets written. I probably didn't need the case. You're right. Okay. There's also a little bit more information we get out of a Sprague-Grundy value. If you think about this in terms of NIM, a single pile NIM game is very boring. The player whose turn it is should just take all the coins and win. But a Sprague-Grundy value kind of encodes how many different losing options you have, which is not terribly interesting for a game like one pile NIM, but it's really the secret to playing a multi-pile NIM game. because if you take the Sprague-Grundy values of the individual piles and do a bitwise XOR, you get the Sprague-Grundy value of the overall game. So if you ever go onto one of these online simulators where they have NIM piles 1, 3, 5, and 7, you do some XOR calculations, you can always beat the computer, but let it go first. And then we kind of get into the game that we looked at is Juniper Green, which is an impartial combinatorial game. And essentially you have a board with a bunch of numbers on it. This was designed for middle schoolers. And the first player picks an even number, and then players alternate turns. Every choice has to be a factor or multiple of the previous number. And you can't pick a number that's already been used. So the goal of this game obviously is to make your opponent pick one so that you can pick some very large prime number and they will lose. So the direct method for calculating the Sprague-Grundy values of this is a recursive procedure where we just kind of run through this entire position graph and we, find those directly. And it's very slow, as one would expect, because, we have exponential growth on the position graphs. So Julien Lemoine wrote this lovely paper last year. It's in French, but it's still worth a read if you can handle French, where he used this concept of an adjacency graph. I'm not sure he calls it that, but I do, where you just set up a graph of when two positions are adjacent, if one is a factor or multiple of the other. And he does this lovely analysis, figures out whether or not the first player can win for every value of n. It turns out that the last losing position, I think, is n equals 118. And he just kind of prunes this graph as he goes along. So you pick a number, the next player picks, we throw away all the parts of the graph that are no longer accessible, and, very nice analysis. And he notes that since if you select one, you lose, he starts out by making this lovely decision to delete the vertex 1, because you would never go there, and also take out all the primes that are attached to it and only it. So all the large primes, because that doesn't affect who wins the game. And it seemed like a natural thing for us to try and do that. Sadly, it doesn't work, because while removing 1 and 5 and 7 from this graph does preserve who wins, it does not preserve Sprague-Grundy values. And the reason for that is really because in this graph, if the first player chooses 6, the second player can make the very silly choice of picking 1 and therefore has a way to throw the game away. But if in this version, the first player chooses 6, the second player doesn't have that silly losing option, and that changes the Sprague-Grundy value. So we could not do that. The one improvement that we did manage to make is, instead of recomputing what moves are legal from each position, I kind of used the adjacency graph idea, stored it once, and then if I want to find where I can go from a particular position, I just take all the vertices that have already been visited and I subtract them from this set and I'm good. So that sped things up a bit. I could only get out to about 35. I think 35 took something like 15 hours to run, and 36 failed at 18. So I decided at this point that since I know I'm not going to find any kind of periodic behavior here until I get past 118, it was time to abandon ship until I find a smarter way to do this. So those are my first 35 Sprague-Grundy values. They're not terribly exciting, and it probably should be. I think I have enough data there that I should submit that one. So we looked at 2 new variations. We have a factor restriction variation where we add the parameters A and B. And so instead of being any factor or multiple, now I can divide by at most A or multiply by at most B. And we wanted to see if this would do anything interesting. In the case A equals B equals 2, this becomes uninteresting fairly quickly. And the reason for this is because if you can only multiply or divide by 2, the first player picks something and the second player chooses a direction to go multiplying or dividing, and there are no choices for the rest of the game. So this devolves quickly. A little more interesting is A equals B equals 3, where you can multiply or divide by 2 or 3. And what I see here is I see a bunch of alternating blocks of 3s and 4s. They alternate for a while. I suspect that they'll continue to do that, but I don't have a conjecture for the block lengths. A equals B equals 4 kind of does the same thing. I see these alternating blocks of 3s and 4s after some initial string. I don't know what they do. We looked at some asymmetric cases. And here I have several hundred 3s in a row. So I think that this sequence may actually not, do anything different. Here, I do see, a little bit of alternation, but then there's a block of 4s that goes from 335 to 500, and I haven't gone past that yet. So that turns out to be not as interesting as we hoped. The additive variation is pretty good. Here, instead of having a maximum divisor or multiple, what we do is we have sets A and B, and you can either subtract an element of A or add an element of B. So, for equal singleton sets, so that is to say, I can only either add or subtract a particular number. Again, this isn't so interesting because the first player makes a decision, the second player picks a direction, and you just keep going in that direction until the game ends. But I did figure out that this is the sequence of Sprague-Grundy values that I see. These exponents are number of repetitions. And this kind of makes sense, right? These zeros show up at even multiples of m, which is the number that I can add or subtract, because at an even multiple of that, whatever number I pick, there's an odd number of moves left in one direction and an even number in the other. Therefore, the other player can always beat me if they want to. Yeah, I mean, there's actually a proof of this in my dissertation. So, and then, when these are distinct singleton sets, it's a little more interesting, but sometimes you get a block of number of used numbers in the middle and you can't go past that. So just reporting some things that I saw here. So if the set A is 1, so you can subtract 1 or you can add B, where B is some larger number. These are the sequences of Sprague-Grundy values that we see. And again, these exponents are just so it would fit on a slide. This is just 3 copies of 2 and 4 copies of 3. And I see a couple of things here. For even K's, the Grundy values are eventually constant at 3, and for odds, they are periodic, and the cycle is K3s and a 0. I'd like to see more data, but that will take more time. Yep.
I was trying to type them at we have -7 minutes there.
I know I have -7 minutes. I will be done in like 2. So I'll only take -9. Okay, so just a little more data. These are unequal singletons where one of them is 2. If I allow 2 element sets with 1 in K, this is what I see. I just have one more thing that I want to say because it might make Bargev happy. And when I do 2 in K, I see this. And I'm really hoping that the reason these cycles are the ones that have period greater than 2 are because 2 and 4 have a GCD that isn't 1. And they're the only ones on here where that's not true. So because these aren't relatively prime, I think that affects the cycle. And again, I'd like to, in future work, generate more data so that I can figure out what's going on. So, and again, I would like to come up with enough data on these to put them in OEIS. And now I can stop. So thank you all.